Morning, guys. I hope you're all having a good, not vacation because it's not vacation, but a good uh, self distancing. I'm praying for all of you guys. I hope you're praying for me. Pray that I get lots of work done in my house because that's what I'm doing when I'm not doing schoolwork. I'm at my house doing work on my new house. So pray that that goes well. I'll be praying for all you guys. Well, today in our science lesson, we're going to be starting Chapter 13, Forms of Matter and Energy. That chapter starts on page E48. And the first lesson, lesson 4, Mixtures and Solutions, starts on page E50. But as we do, we're going to go straight to E52. First, we're going to learn what a mixture is. There's a difference between mixtures and solutions, as this chapter indicates. A mixture is a more general term. A mixture is something that is physically combined. You could have a mixture be something like a tossed salad with tomatoes and onions and lettuce. A mixture could be, when you're making cake batter and putting the flour and the milk and everything, those are mixtures as well. A mixture is a more general term. So the first word, you see it in yellow highlighted on page E52, is the word mixture. And the key is that it's physically combined. We're going to talk about things that are chemically combined further in the chapter, but for right now we're talking about physically combined. What physically means is that you take something and you put the two of those things together and smush them together, mix them up, do whatever, and that's physically combined. If you see in the picture down below, two things are chemically combined. You see iron disulfide. Iron disulfide, and that's chemically combined. The only way it can be separated is by a chemical change of some kind. There you see it's changed by magnetism. You bring the magnet there, the iron leaves the sulfur, and you have iron and sulfur by themselves afterward. But so let's talk about physical mixtures, though. I encourage you to keep reading, and you're going to be reading the entire chapter when you do the lesson outline in a little bit. But let's go to page E54. Let's talk about different kinds of mixtures. We have heterogeneous and homogeneous mixtures on page E54. Heterogeneous and homogeneous. The word parts, I always encourage you guys, especially in science, to look at the word parts, especially prefixes. Hetero meaning different and homo meaning same. Heterogeneous mixture are things that look different, and homogeneous mixtures are things that look the same. It has to do with what they look like when you look at the mixture. A homogeneous mixture looks all the same throughout it, and a heterogeneous mixture is something that might have speckles or dots or something like that. So there are a couple examples that I used before. Something like a tossed salad is a heterogeneous mixture because it's not completely evenly distributed. It doesn't look the same throughout. You might have one part of the salad with a little bit more tomatoes, another part of the salad with a little more croutons, depending on what you like in your salad. If you're one of those weird people like cranberries and all the crazy stuff, you could have some cranberries in there. That's a heterogeneous mixture. It doesn't look all the same. It's not evenly distributed throughout. It could look speckled and everything like that. It might be cloudy. A homogeneous mixture looks all the same everywhere, as if everything is blended completely. It looks like one thing. If you didn't know better that it was two things mixed together, you would think it was just one thing. And we have a special name for this called a solution. So solution is the same thing as a homogeneous mixture. There's on page E55, you have different types of solutions. A liquid solution, you can have a solution can be a liquid, gas, or a solid. Usually we think of solutions as liquids, but they can be a gas or a solid. A solution would be something like cranberry juice dissolved in water, water dissolved in air, and mercury dissolved in silver. That would be liquid dissolved in liquid, would be a cranberry juice dissolved in water, so it's liquid dissolved in liquid. Liquid dissolved in gas is water dissolved in air. Liquid dissolved in solid would be mercury dissolved in silver, like in dental fillings. Although nowadays they don't really use that as much anymore. You can still get that It's a little bit cheaper, but a lot of times they use this white stuff instead of having like a silver tooth. Another type of solution would be gas dissolved in things. So gas dissolved in liquid would be gas dissolved in carbon dioxide, which is a gas, which is, remember, the gas that we breathe out. That's carbon dioxide, CO2. Carbon dioxide under pressure dissolved in water to make soda. If you're drinking soda, they take the gas and they dissolve it into the soda. And unless you shake it all about, it does look the same throughout it, and so that would count as a solution. Then you have gas dissolved in gas. The air that we breathe is oxygen and nitrogen. It's mostly nitrogen. I know we think of oxygen as the air being oxygen because that's what we breathe in, but it's only about 20% oxygen. Most of it's nitrogen. It's like 70-something% nitrogen. And so those two things together, air itself is a solution. It's a gas dissolved in a gas. And then a solid dissolved in a liquid would be like salt dissolved in water. You can have a certain amount of salt that you dissolve in water. I don't know if your parents dissolve salt in water in order to boil water. They might do that because what that does is that, remember from last chapter we talked about boiling point. When you put salt in water, it actually changes some of its properties and brings the boiling point down lower, so it doesn't have to get all the way up to 212 or 100 degrees Celsius. It can get lower in order to boil. A solid dissolved in a solid, there would be copper and zinc mixed in brass. That trumpet there that you see in that picture is made of brass. A lot of brass instruments. They have a whole section of instruments called brass instruments. Trumpets, trombones, tubas, they're called brass instruments because they're made of brass, which is copper and zinc. Copper and zinc mixed in the brass there, but they're mostly brass. So those are solutions. Solutions are basically, they're mixed all the same throughout. They can be solid, liquid, or gas, but they look very similar all throughout it. And those are types of homogeneous mixtures. Remember, heterogeneous look different. The next yellow word that you see there is the word colloid. Colloids are things that are in between homogeneous and heterogeneous mixtures. They don't really have the properties of being completely, they look almost like they're blended together. So they almost look like they're homogeneous mixtures, but they're not quite homogeneous mixtures. We have different types of colloids. You could have them based just like we had with solutions. You could have one state of matter dissolved in another. So a liquid dissolved in a liquid would be something like mayo. A liquid dissolved in a gas would be something like clouds. What liquid is dissolved in what gas to make clouds? Water, which is the liquid, dissolved in air, which is the gas, and that's a colloid. Because if you picture all these colloids that I'm describing, they're one of the ways you can tell it's a colloid is that it doesn't really fit into easily fit into a state of matter most of the time, such as a cloud. If you were to say a cloud, is it a liquid? Is it a solid? Is it a gas? It's kind of difficult to figure that out. Mayonnaise. The next one, jam. Liquid dissolved in a solid would be jam. You have different types of colloids here. Gas dissolved in a liquid, like shaving cream. That's like a foam. Is foam solid? Is it liquid? Is it gas? It's difficult to say. So gas dissolved in a liquid. Basically, you take a liquid and you dissolve a gas in it. You pump in a gas, and it gives it that puffy look. Same thing with whipped cream. Gas dissolved in a solid would be marshmallows. You take a solid and you put gas in it. It makes it light and airy. Obviously, you'd consider a marshmallow a solid because it's close enough to actually be a state of matter. But it has a gas dissolved in it, so it counts as a colloid. And a solid dissolved in a liquid would be toothpaste. When you think about toothpaste, it's very difficult to, is it solid? But it's almost like a liquid, but it has too much structure. You see, you take the liquid toothpaste and you put some structure in it for a solid. And a type of colloid, the last type of colloid would be a solid mixed in a gas, would be smog. And so that's those are the types of colloids right there. We have, if you move on past page E55, we have You can continue reading. I want you to read all of it. And there you have talks about the different 78% nitrogen, 20% oxygen in gas. Of air, and a lot of different types of kinds of solution. They're just examples. But if you look at page E57, we have two words that they bring up called solutes and solvents. And so those are two important things in a solution, the solute and the solvent. It's basically the two parts of a solution. A solute is dissolved in a solvent. The smaller amount is always the solute. It's the one that's dissolved in the other amount, the solvent. If you think of salt and water, which is one of the examples we gave, salt would be the solute, water would be the solvent. Whatever you dissolve in it, whatever you dissolve, the smaller amount thing that gets dissolved is the solute. Whatever it gets dissolved in is the solvent. A solute is a solvent, and together they make a solution. Solution. What is solubility? On page E58, we talked about the solubility. It's a property. We talked about last chapter different properties of matter. You could have buoyancy. You could have magnetism. You could have density. We talked about all those different properties. Well, solubility is a property of not all types of matter, but a property specifically of solutions. Solubility, it describes the ability of a solute to dissolve in a solvent. Well, what does that mean? Solubility is how it can dissolve. How well can it dissolve, right? How much of it can dissolve in a particular solvent. And a lot of things affect solubility. They list there temperature, the structure of a solute affects its solubility in a particular solvent. For instance, it talks about there that oil will not dissolve in water. That's due to its structure. You can, if you were to take a little experiment at home, if you want to do a little experiment today, feel free, take a little bit of oil. You might take oil for like salad or something like that. Maybe like some sort of oily salad dressing, like Italian dressing or something, and pour a little tiny bit in the cup and pour a little bit of water in the cup. And you'll notice you can kind of shake them up a little bit and they get a little bit mixed together. But if you leave them for a while, they will separate because oil is not soluble at all in water. As I said before, salt does dissolve in water, so salt is soluble in water. There's always a limit. If you were to pour a gallon of salt in a cup of water, the first little bit of salt would dissolve in the water, but after that, there's going to be a whole pile of salt at the bottom. So there's always a limit to the solubility of water, and so it becomes the word that's used when you dissolve the maximum amount of solute in solvent is saturated. If you have, once you reach, there's always a maximum. Let's say for 1 cup of water, there's a maximum amount of salt that you can have. It's not a 1-to-1 ratio. It's not exactly the same amount of water as the exact same amount of salt. But if this is the limit of the amount of salt that you can dissolve in water, you keep going and keep going, more and more and more dissolve until you reach that threshold. Then the second you reach that threshold where it's 100% of the salt is able to be dissolved and no more salt can be dissolved, that's called saturated. When you get beyond there, the word part becomes supersaturated, because the word super means above. It's opposite of sub. Sub is under, super is above. So it becomes supersaturated. You might hear somebody talk about something as supersaturated. The air could become supersaturated. It means too much water in the air. It's really, really humid. But supersaturated means there's too much. It can't be dissolved in it anymore. So let's talk about on page E59, heterogeneous mixtures. So everything we talked about so far, they're the homogeneous mixtures, otherwise known as solutions, where it's blended all the way throughout. Now let's talk about heterogeneous mixtures. A perfect example on page E59 is that rock that you see on the top of the page. As you see, it's pretty obvious that thing does not look completely blended and completely the same throughout. Heterogeneous mixtures are way more common than homogeneous mixtures. We see them all throughout our day. I mean, you could consider your dirty laundry that's sitting in the corner of your room right now a heterogeneous mixture. because they're all lumped in together, but they're not all blended completely. Heterogeneous mixtures in a liquid are often cloudy or opaque. The word opaque means that you can't see through it. Like, my hat is opaque. You can't see through it right now. That's opaque. And so oftentimes if a liquid is opaque, meaning you can't see through it, you can't even see light through it, because if you can see light, it's called translucent. If you can see through it clearly like a window, that would be transparent. But opaque means you can't see anything through it. If it's a liquid like that, a lot of times it would be considered heterogeneous. But, and I brought up oil and water before. Oil and water would be considered a suspension. That's the next word that's highlighted in your book there. A suspension is one thing that you try to dissolve it, but it sits one on top of another. They do not mix together. When left alone, they completely separate. And you can see in that picture, both clay and water and oil and water, when you shake them vigorously, at the picture at the bottom of E59, when you shake them vigorously in the left picture, you can see that they look like they're mixed and dissolved in one another. But if you leave them alone for any point in time, if you look on the right, the water and clay separate and the oil and the water separate. Interestingly, with the clay and the water is on top, notice. With the oil and the water is on the bottom. Now, what does that due to from last chapter? Anybody remember what that's caused by? If you said density, you're correct. The density determines where each one of them are, and so obviously clay has a higher density, a bigger number than water. Do you remember what water's density is? See if you remember. The density of water is 1. And so it's given the number 1, 1.000. And so clay must be, that clay right there must be something, I don't know what it is, but something over 1. And the oil, notice the oil is above the water, so that means that its density is lower, so it has a number somewhere lower than 1. And so those are suspensions. Page E60, they talk about different types of colloids. We went over some examples of something dissolved in something, but some colloids have special names, special categories. And I'm not talking about like toothpaste and stuff, but they have special categories to these colloids. The first one they talk about is, the first highlighted word is called an emulsion. An emulsion is a liquid spread through another liquid. That sounds kind of gross, might sound really gross to you, but what milk is fat, liquid fat spread throughout liquid water. So it's a liquid spread throughout another liquid that doesn't become a complete solution. Almost as like a solution. It's almost, homogeneous mixture, almost the same throughout it, but it's not quite a solution because it doesn't follow all the characteristics of a solution. It's not. It's kind of a milk, you can't really see through it. It's kind of cloudy and everything, and so it's kind of between a homogeneous and heterogeneous mixture, which is why we call it a colloid. And so the liquid spread through a liquid is a special colloid called an emulsion. And again, that's milk, which is fat spread throughout water. Sounds very appetizing. I had some fat water with my cereal this morning, and so kind of gross, but that's what it is. Anyway, next one. The next one is called an aerosol. An aerosol is when you take either liquid or solid particles and you dissolve them in a gas. So it's essentially like a gas with little liquid and solid particles in it, so they can be sprayed somewhere. You might find an air freshener is an aerosol. You might find what does it tell me there? Fog. Yep, fog is a water, which is liquid, spread throughout a gas. Anything really that you spray, hairspray would be an aerosol. It's usually a lot of times in pressurized containers. Those are aerosols. The next one is called a gel. Gel would be like Jell-O, is an example of a gel, and that is a solid put into a liquid. So you have a liquid is the main component, and you add a solid to it to give it more structure. It'd be like Jell-O, it'd be like toothpaste, different things like that, gelatin. And the last category of colloid is a foam. A foam is where you take a liquid and instead of putting a solid in it to give it structure, like we did with gel, you put a air in it to give it more of an airy structure, like you'd have with shaving cream or whipped cream. Now notice they have shaving gel and shaving cream. Shaving cream would be considered a foam. Shaving gel would be considered a gel. They basically do the same job. If you watch your dad shave or something like that, they basically do the same job, but they're two completely different types of colloids. Anyway, and E62 is a little bit of a long chapter. I'm on minute 20 here, but hopefully you are still engaged. How can mixtures be separated? We're going to talk about different ways you can separate mixtures, and the ways that you can separate mixtures completely different based on what they are. I mean, you can if it's a really really heterogeneous mixture that's really easy to. I mean, as I said, your dirty laundry at the corner of your room, just pull them apart. A salad in a bowl, just pull the ingredients apart. But some things are more difficult based on a lot of their properties. The first example they give is sand and salt. Sometimes you have to really think about how you do it. A mixture of sand and salt. Obviously, I mean, could you separate them physically and take every single grain of sand, put it on one side, every single grain of salt, put it on the other? You could do that, theoretically. It'd take a really long time, though. So you have to think about, what do I know about each of these things? Well, what I know about sand and salt is that, as we stated on previous pages, salt dissolves in water, sand does not. So if I know salt dissolves in water, if I pour enough water in it that all of the salt dissolves, then I will be able to pour a bunch of water and all the salt dissolves. And so what I have from there is salt water and then with sand at the bottom. Okay, so the salt, it dissolves in the water. And that's step one. You pour in a lot of water. You fill it up and all the salt gets dissolved. You kind of stir it around a little bit. All the salt gets dissolved in the water. The sand does not. And then and then afterwards, so you have this mixture that's salt water and then sand at the bottom. Then what they do is that they use a filter paper and they pour the entire thing through the filter paper. Well, the salt that's dissolved in the water goes straight through the filter paper. Now, salt wouldn't necessarily go through the filter paper, but since it's dissolved in the water, now it can go through the filter paper, and the salt water mixture goes all the way through into another container below, and the sand stays on the filter paper because the sand is larger particles at this point. Then afterward, you have now the sand on the filter paper separate from the salt water. Well, how do I get the salt back to be just regular salt? It's salt water right now. How do I get it back to be regular salt? By evaporation. We know that water evaporates. Salt doesn't evaporate. So you put the salt water in some place that it's going to evaporate. The water leaves and the salt is left behind. And now you're left with sand and salt. That's a lot easier than picking out individual particles. I don't know if you can hear my children. My children are singing right now. Separating sand and wood chips. We see the top of E63. We have sand and wood chips. This one's a pretty easy one, but you'd have to, again, think about the properties of each thing. What do we know about sand? Sand sinks in water. What do we know about wood chips? Wood floats. If you take a piece of wood and put it in the water, it's going to float on top. Like that's how they used to get logs down the river back in the old days when they cut down trees. They would cut down the trees, knock them over, send them straight down the river. So if you have sand and wood chips, if the wood chips are big enough, you could just pull them out of the sand if there's not enough of them. But if they're all mixed together, wood chips are really small, you might have a difficulty with it. Pour water in, mix it together. The wood chips all float on the water, and the sand is on the bottom. The last example there, and these aren't the only examples. These are just ways that you can think of it. You have to think about the properties. We say separating alcohol and water. By alcohol, it means anything that, if you see a chemical formula, anything that ends in OH is considered an alcohol. Anything that ends in, the name of it ends in OL, like ethanol, like you might see that at a gas station, that's considered in a category of alcohols. Well, alcohols are one of the properties of alcohols is that they have they evaporate very, very easily, and they usually have a low lower boiling point. For instance, we know that water's boiling point is 100 degrees Celsius. The boiling point of alcohol might be 92 degrees Celsius. So what we could do there, this seems like a little bit complicated at first, but if you look at this picture on page E63, we have the original alcohol and water mixture. They are together right here, right? They're in the same beaker. What happens is it gets evaporated here, okay, and the vapors cool and condense. What happens is the alcohol, and they're both heated, so alcohol boils at a lower temperature than water. So at the beginning, more of the vapor will be alcohol than water. So what the vapor comes down and it condenses back into a liquid down here. Well, most of it will be alcohol, because if you were to keep, theoretically, let's say you were to keep let's just say, I don't know what the alcohol that they're using is, but let's say the boiling point of the alcohol is 92 and the boiling point of the water is 100. If you were to keep that flame going at 95 and the temperature of that solution to be 95, then what would happen is all the alcohol in the solution would be boiling off and becoming a gas, where the water isn't quite to the point where it boils yet. So all the water, at least most of the water, would be staying still. You're always going to get a little bit of evaporation no matter what, but the alcohol would evaporate and go into that place, and as it's going down that tube, it would cool down and turn back into liquid in the other beaker. The water would stay a liquid in the beginning. So again, all of these principles are knowing the properties of each of these items that we have. So that's different ways you can separate mixtures. And again, those aren't the only ways you can do it. I mean, you could, I know there's distillation and stuff like that. Sometimes you can, if it's a suspension, you might just simply be able to pour, oil and water. You might be able to pour them and get the top one to slide off of it. There's many different ways you can do it, thinking about their properties. So we're not going to talk about E64. You don't have to worry about that. It mentions distillation a little bit. You can read about it a little bit there, distillation, but I'm not going to cover it here. You're going to be seeing soon, you're going to be having to do the lesson outline on the practice book pages. Tune in for that. I'll be praying for you guys. I hope you're praying for me. Keep in touch on RenWeb, and see you guys later.